And so today we're going to be discussing electrochemical cells, batteries, and this is going to be a lot of review. So today it's going to feel like a nice warm blanket of Chem 1 stuff, balancing redox reactions. Don't you like it when we go back to the basics? It's like, I kind of remember that, but I forgot that little piece, and that's an important piece. So it reinforces the basics. So let's dive in. These are non-equilibrium systems because we set up these concentrations in the battery, and we don't want it to be at equilibrium. We want it to try to get to equilibrium. And the way a battery tries to get to equilibrium is by pushing electrons through our circuits. So that's where we get the useful energy out of a battery or electrochemical cell, is that we have set it up kind of potentially or electrically uphill, and then we put our circuit between that battery and where it wants to be. So we talk about electrical potential. It's directly related to the Gibbs energy. So this is a fantastic equation. We've dealt with Gibbs energy this whole semester, and now we can convert Gibbs energy into electrical potential. So remember, spontaneous cells have a negative delta G. Okay, a spontaneous reaction with a negative delta G. You change that sign, you get a positive cell potential. So batteries with a positive voltage have a negative delta G, and that's what's driving them forward. They're spontaneous. So that's one of the principles this morning to put in your memory. Positive cell potentials are spontaneous. Now we have a couple of other constants in this equation. We have an N, which is the number of electrons or moles of electrons that are transferred in this reaction, and then F is Faraday's constant. So this is a constant we haven't used all semester. This is using counting how many coulombs or units of charge there is in a mole. And it's also the conversion of joules per volt mole. So the joule per mole, the energy per volt. So that's the conversion of Faraday's constant, and it's useful in this. So what that does is it converts the joules per mole of electrons, okay, in this delta G over to volts, which gives us the cell potential. And so we set up this reaction. We have the standard delta G, which gives us the standard cell potential, and then we have the actual delta G and the actual cell potential. So the difference between standard and actual would be the standard conditions of room temperature, 1 atmosphere for all the reactants and products, and 1 molar concentrations for anything that's aqueous. So those are the standard conditions. And then anything different than the standard conditions gives us the actual delta G and the actual cell potential. And so what is the system at equilibrium? The actual delta G at equilibrium is 0. Okay, so you can have a standard delta G and an actual delta G, and if you have this standard delta G for a reaction, and then the actual delta G at equilibrium is equal to 0, then this Q, the reaction quotient, becomes K. So at equilibrium, Q becomes K, those equilibrium concentrations and partial pressures. And then since it's 0 on the left, then you can rearrange this, and that's how we have our relationship between delta G and the equilibrium constant, which you've used so much already. Okay. But dealing with electrical potential, we take this substitution up here in Fe and put it in to our equation. And so we have the cell potential that's the standard cell potential, using 1 molar concentrations and 1 atmosphere pressures for any gaseous reactants or products. And then we have the actual concentrations in this reaction quotient here, and that gives us the actual cell potential. So we can change the cell potential by changing the concentrations of the reactants and the products. This leads to the Nernst equation, and so that's what we'll talk about here. The Nernst equation uses the standard conditions, 298.15 Kelvin, and you put that in with the gas constant and Faraday's constant, and you end up with this number, this 0.02569 volts. Then you have using the natural log, so substituting that natural log into base 10, you end up with the Nernst equation. So this 2.303 times this 0.025 gives us the 0.05917. So if you look up the Nernst equation, you'll have this number up here. And I'm just showing you where it comes from. Okay. And so then this Q, that's the reaction quotient. So let's look at an example of that. So far all our concentrations for these standard cell potentials have been 1 molar. But remember, if we change those things, we can use the Chatelier's principle. So let's look at this reaction. So aluminum in contact with manganese ions will spontaneously oxidize and become aluminum ions, and the manganese will precipitate out, become solid. So this is a spontaneous cell. It has a potential of about 0.5 volt. Okay. But if we change those concentrations, we'll change from the standard cell to actual cell. So this is a question here, kind of a mini Kahoot right here in the lecture. If I make the concentration of aluminum in solution, aluminum ions, 2 molar, and leave manganese at 1 molar, what will happen to the actual cell potential? Will it be greater than the standard cell potential or less than? What's your reasoning on that?
Because like N is in the denominator.
What's in the denominator?
The number of moles.
Number of moles? Okay, that's the number of moles of electrons for N that's exchanged between the two. And so in this case, we're looking at the concentration of the aqueous things. Because for the standard cell potential, so this cell potential is based upon 1 molar here and 1 molar there. That gives us this voltage. Okay, and what have we done? We've doubled the molarity of which substance? Aluminum, which is a product. So what do you think that will yield? It'll be less than. And why would it be less than? Yeah, it's. Let's use the word spontaneity. Why would it reduce the spontaneity? There's already product there. Yes. And so it's going to reduce the push of this reaction in the forward direction. And so, yes, you got that right. Less than. So the actual cell would be less than the standard cell potential. If we wanted to increase the standard cell potential, we could make the manganese 2 molar. So we could put aluminum metal in contact with a more concentrated solution, and then we would drive that reaction forward in a stronger manner. We can make a higher voltage cell. So the standard cell would be 0.48, but if we doubled the concentration of the manganese, it has a logarithmic determination, so it would raise it by the natural log of 2 times that constant, and so on. So it's not just, it wouldn't double the cell potential, but it would adjust it up. It would make it higher. And so galvanic cells are not at equilibrium, so we use that Q, that reaction quotient. Now notice we only put in the reaction quotient the things that can change, the aqueous concentrations and partial pressures of gaseous substances. So we don't have any solids, we don't have pure water. If water is part of the reaction, we don't put water concentration, because this is the concentration of the substance in its medium. All right, so aqueous solutions, it's the concentration of aluminum ions in water, because that's what aqueous means. But for aluminum solid, that would be the concentration of aluminum in aluminum, and that's a constant. So it's lumped over into the constant side of things. And same with water, liquid, that would be the concentration of water in liquid water, also a constant. So we're only putting the variables in our reaction quotients and in our equilibrium constants. Okay. So let's do an example of the Nernst equation. That same cell. So if we put in the 0.01 molar aluminum and 2 molar manganese, we have the Nernst equation. We have 6 electrons transferred. If you'll notice here, we have 3 times 2 plus, and that produces 2 aluminum ions that are 3 plus. So there's 6 electrons that have changed place, and so that's this 6 down here. We have the concentration of aluminum on top, concentration of manganese on bottom, and when you take in the squares and the cube and the log, you end up with an adjustment. So this piece right here gives us a positive 0.07 volts, so it raises it up a little bit. So it is sensitive to concentration, but it's not that sensitive. I mean, we really put 2 times in 0.001. We've really swung the concentrations quite a bit, and it only adjusted by 0.07 volts. So that galvanic cell reaches equilibrium. As it reaches equilibrium, then the Q will go to K, and this will cancel out that cell voltage, and you'll end up with a 0 actual voltage. And so if you were wanting to really be deceptive to people, you could sell extremely safe, pre-equilibrated batteries. Right? They would be extremely safe because there's no cell potential there anymore. It's just a chunk of metal. Okay. They wouldn't run anything. You'd probably have a very short-lived business. Okay. So let's look at what's going on. It's a voltaic cell. And so we have these dissimilar metals put in electrical contact with an electrolyte, some sort of solution that can conduct ions. And then it sets up a potential, and the mobile species through the solution is the ions, but through a wire is the electrons. And so the electrons go on one path, and the ions go on another. So in this case, you have a salt bridge. You don't really need a salt bridge. You could have a glass frit, or you could have it in the same solution. But zinc, the anode, it is actually decreasing in mass. Zinc metal is leaving that electrode, so it will shrink. It will eventually disappear, and the battery will be dead. So the zinc ions go through the salt bridge. Over here, copper in this copper solution. This copper electrode is growing in mass because copper ions are becoming copper solid. So notice I've drawn the positive path. So the positive ions are going this way. If we draw this in a circle, the positive ions are going counterclockwise, and the electrons are going clockwise. So negative ions are going this direction, and then the electrons are going through our circuit. So cations are called cations because they're attracted, or they're mobile, or they move towards the cathode. So that's where that came from. That's why they're not cations. It's a cathode, and we call them cations because they're moving towards the cathode. And the anions are moving towards the anode. So we had the word anode first, and then we defined those ions that move towards the anode as anions, not anions. So you look at those terms. I've heard people say the anions and cations, and I'm just surprised. Okay, so then what's going on at the anode is the oxidation. So we have zinc metal, zinc solid going to zinc cations, and then what happens at the cathode, we have reduction, copper cations becoming copper solid. So they're being reduced. They're gaining electrons, and then the reduction is losing electrons. And so you have oil rig. Oxidation is gain of electrons. Oxidation is gain. No, oxidation is loss of electrons. Oil. See, that's why you have the mnemonics. And reduction is gain, rig. Okay. And another thing, too, how to remember which of these little things dips down, which one's the cathode, which one's the anode. I came up with this. So this is a DW original. You got to have something that you're proud of, right? And so this is over here, the oxidation reaction, and there's this anode that goes down into the beaker. And over here, this is the reduction reaction, and there's a cathode that goes down into the beaker. And so you can put cathode on the word reduction, but you can't put cathode anywhere in the oxidation. Isn't that cool? Oh, come on, give me some help. Okay, and then anode can go in the word oxidation, but it can't go in the word reduction. So, and the anode and cathode go down in the beaker. So you could draw the little beakers down here like this. Okay. Oh, that's a bad beaker. Okay, and then a salt bridge. Okay, and then the wire. Yeah. So it's just. Yes.
The to be or not to be last semester.
Okay, that was better. Okay, thank you. All right, 4B, 2B, 4B if it's Raman. Yes. Okay, well, I'm very proud of this. I don't know. Yeah. So we have then we've set up a standard in terms of this reduction potential, right? What is essentially 0 volts? Because for delta G we had a standard. We had a standard that was elements in their standard states for delta G of formation. So if it was O2 gas, oxygen, pure element, a gas, room temperature, 1 atmosphere, then we're going to call that delta G of formation 0. So anytime you have this scale, you want to have a 0 point on your scale. What's the origin, right? You measure everything relative to this reference point. And so they chose the reference point as hydrogen gas, the reduction of hydrogen gas. So acidic solution, adding electrons to those acid protons and producing hydrogen gas, that is our 0 for volts. And so that's defined right here in this reduction table as this reaction of hydrogen gas being formed from acid protons. And these are all reductions in this table. So what is the potential for all these other reactions relative to that hydrogen reaction? Now that we've defined one as 0 volts, we can put that reaction in contact with all these other reactions and find out what their voltage is. And so the highest voltage on this is fluorine gas going to fluoride. Okay, you can reduce fluorine gas and make it fluoride. That's plus 2.87 volts, so very, very favorable reaction in that when compared to hydrogen. So if you put fluorine gas in with hydrogen gas, it's going to be very spontaneous. It's going to produce HF. Okay, so what we have, if you think about this, is forward reaction up here would be a reduction, and then a reverse reaction would be an oxidation. And so clockwise loops in this table, because they're sorted from high to low, so notice this over here, because they're sorted from high potential to low potential, clockwise connections in this table are all spontaneous. So in this case, we have the forward reaction of acid protons becoming hydrogen gas, and down here we have the reverse reaction of lithium metal becoming lithium ion. So reverse this, that's an oxidation reaction, because lithium is losing an electron when it goes past this arrow in reverse. And so the oxidation paired with the reduction makes a cell, makes a redox reaction. And that would be a positive cell potential, because down here this one's negative, but if we run this reaction in reverse, then it's positive. And so we have the reduction, and we have minus the negative 3.05, so we have a positive cell potential of 3.05 volts for lithium metal becoming lithium ion and hydrogen ion becoming hydrogen gas. So if you'll notice, any of these metals below hydrogen would produce H2 gas spontaneously in acid. So if you put acid in contact with nickel, it's going to spontaneously generate hydrogen gas. So it's a really big problem if you're storing acid in a nickel-lined tank, okay, or running it through a nickel tubing. If you don't know about the activity of metals, then you're going to make a big mistake, and this has industrial consequences. They put nitric acid in an unlined stainless steel tank up at Boeing in Tacoma, Washington, and had to evacuate the whole plant because it started reacting and making nitric oxide and also hydrogen gas inside this tank, and it blew the top off the tank, and this brown gas came out, and everybody, they shut down the plant and had to clean up the mess because they didn't pay attention. They thought they could store strong acid in a stainless steel tank, and you can't. You have to have a glass lining because of this.
Isn't that similar to like what happened with like flint and like other like lead piping?
I'm not sure. Yeah, I mean those metals are, depending on the pH of the water, more or less soluble, and so it may be. I haven't done the research on that, but I know that they did have leaching of lead into their water system. I don't know if it was because of the acid.
It was like they didn't put in some chlorine thing or something into the water system when they were circulating it.
Okay.
So it like caused the pipe lining to come out into the water.
Oh, yeah. No, this is just more focused on the activity of these metals to produce hydrogen gas spontaneously, but they might just become soluble based on other reactions. Notice any of these other reactions up here, like if, well, that's got acid protons, but I mean, you could pair any of these metals with any of these reactions above it and produce hydrogen gas or produce cations. So you would dissolve the metal.
I remember like when I was in like high school chemistry, and I was talking, we were going over this in that class, and my teacher was talking about how like you could push back oxidation by having a metal that's like high iron potential?
Yes, so you could put in, that's another interesting thing. Let's forget about hydrogen and let's just put, let's see, there's a famous one. Well, copper and iron right here. So for the Boy Scout merit badge, we put iron in contact with copper. And so notice this is a clockwise reaction, so draw an arrow there. So if I have copper solution, so copper sulfate, blue solution, and I drop a metal, an iron nail in there, the iron goes into solution. So see the iron here is oxidized spontaneously, becomes iron 2 plus ion in water, and then the copper is spontaneously precipitated out. And that's called a metathesis reaction or exchange reaction. So the solid and the aqueous, basically they change states. Iron becomes aqueous and copper becomes solid. And you just see this copper sponge grow on the metal. And if y'all want to do that, I have all that stuff upstairs for the merit badge. You can put it in a vial and watch it grow. And it looks like it just grows this orange or, copper colored sponge on the iron nail. And the solution goes from blue to yellow through green, where you have blue and yellow together, but then eventually it becomes yellow, which is the color of the copper ion. The iron ion in solution. And so these electrochemical reactions are key because they exchange electrons. So this is a reduction, oxidation, or redox reaction. So let's go through balancing redox reactions. This is the review part, the strong review part. And the way we balance redox reactions, because we can't always see the number of electrons being transferred, is to go through this in a two-step process. We treat each reaction as a half reaction and break those apart, balancing each half reaction independently. So we break the reaction into two half reactions, and we'll practice one here in a second. But these are the rules. If you will save this slide in your pocket, anytime you're faced with a redox reaction, you'll be able to balance it. Okay. You balance each half reaction in the following manner. You balance all the elements other than hydrogen and oxygen. Leave those for last. Okay? Because you're going to balance the oxygen by using water. So the source of oxygen or the sink for oxygen in these redox reactions is going to be water. It's going to be, and these are all aqueous-based redox reactions, so they have water available to them. And then once you've added water to the reaction, you've brought in more hydrogen. That's why you hold hydrogen off to the end. Because if you're going to balance oxygens with waters, you're messing with the hydrogen numbers. And if you had already changed some things and got hydrogen in balance, when you add water, you're going to screw that up. So let's just hold hydrogen off until after you've balanced the oxygens. Now we balance the hydrogens with acid protons. Most of these redox reactions are acid mediated. If they're not, you'll end up with acid as a product. And then you can change that by adding hydroxides to both sides, and you'll see that this is a base mediated reaction. But most of them are acid mediated. And then you balance the charge by adding electrons. Notice we have to do that last because when we add acid protons, we're changing the charges. And so we have to hold charge off to the end. And then we've got a balanced half reaction and balanced charge and balanced elements and so on. And then we multiply those half reactions by integers so that the electrons gained and lost are the same. This is the coupling that tells us how many electrons are exchanged in one cell of this reaction. And then we add those half reactions and subtract things that appear on both sides. You might have water on both sides in each of the half reactions. When it's balanced, and then you'll end up with it on both sides of the arrow. And it's just like math. You can do anything you want as long as you do it to both sides. So you have 8 waters on one side and 4 waters on the other. You can subtract 4 from both sides. And so let's use this reaction as an example. It's a redox titration of oxalate ions. So if you're trying to tell how much oxalate you have in this solution, you can just add permanganate. The beautiful thing about permanganate is it's both the reactant and the indicator. Because it's bright purple, and if you put permanganate in there and it's chewed up by the oxalate, then the color goes away, as you see on the left. And in the middle, it starts to go away slowly because there's less oxalate, and it has to find the oxalate in solution. And then on the right, 1 extra drop of permanganate, and the thing turns purple. I think they've gone a little further past the end point, but since they were so close here, and look how much more they've added. Anyway, it's easy to criticize. Okay. So we have the carbon half reaction. First, let's look at this. When we say half reactions, most of the time it's obvious what the two reactants are. Okay, it's manganese is one of the reactants and carbon in the form of oxalate is the other. Some weird situations occur where you have a species that's both the oxidant and the reductant. So a lot of the iodine reactions, it can behave as both. So those are tricky, but most of the time it's not tricky. So we have the oxalate half reaction. So we need to balance the elements other than oxygen and hydrogen. So we just put a 2 in front of the CO2 and we balance the carbons. That's easy. Then the oxygen is balanced as well. So we got lucky. We have 4 oxygens on either side. And so we need to balance the charge. Now, this is the thing that is a mental hurdle for some people. They think by balancing the charge means you have to get the charges down to 0, and you can't do that. You can't subtract charges. You can only subtract by adding electrons on either side. So if we have a -2 on the left, there's no way to get that up to 0. So we just have to have the left side equal the right side. And the only thing we can do to balance the charges is add electrons. So we're going to add 2 electrons to the right so that both sides are -2. That's the mental hurdle that most people hit. They get to that point, they're like, how do I get the 2 down? And they'll do something crazy. They'll add 2 electrons on the left and make the situation worse. Okay, they're just not thinking through that doesn't cancel out the 2 negative charges on the oxalate. That just actually makes the left side -4 and the right side still 0. So the only thing you can do is add electrons, and all you can do is reduce one side or the other. So let's do the manganese half reaction. So we balance the manganese. Let's add 4 waters to the right. And so now the oxygens are balanced. This added in hydrogens. This reaction didn't have any hydrogens to begin with, but now it does. And so we've got to put 8 protons on the left side. And that changes the charge situation. So that's why we hold the electrons off to last. And so then looking at this, we have +8 on the left, -1. Okay, so we have +7 on the left and a +2 on the right. Notice we don't have to get it to 0, we just have to get the left equal to the right. And so we just need 5 electrons on the left. Okay, so we balance the charge by adding 5 electrons to the left side. Okay, and this is good because we added electrons to the right side of the oxalate and the left side of the manganate. And so now we know which is going on, which is the oxidation, which one is the reduction. So we check our work by looking at the charges. So we have a -5, +8, -1, and that's equal to a +2. So the charge is balanced. And then let's check the elements too. So we have 8 hydrogens, 1 manganese, and 4 oxygens on both sides. So that checks out. And we've got our balanced half reactions. But we haven't coupled these together. So the next step is we look at them, and we've got to get the number of electrons to be equal. So we had 2 electrons on the top reaction and 5 on the bottom. And then the nearest common multiple of that is going to be 10. It will always work that you multiply each by the other, but you don't always have to. If one is 4 and the other is 2, then don't multiply the 4 one, just multiply the 2 one. And so we have 5 oxalate, 10 CO2s, and 10 electrons. And then 10 electrons, 16 hydrogen or cations, the 2 permanganates, 2 manganese, and 8 waters. And so this is the N in the Nernst equation. So if you were to use this reaction and try to come up with a Nernst equation reaction to calculate the actual cell potential, you would need N. And you've got to do all of this work to get to N. And you couldn't look at either one of the half reactions and know what N is. Because up here you see there's a 2, and here you see there's a 5. Even if you balance the half reactions, you would say, oh, it's 5, or it's 2. No, it's actually 10. And so then we add these together, and we get this total reaction. Notice there's no electrons in the end result because they've canceled each other out. That's the purpose of balancing the electrons. So we check our work with charges. We have a +16 from the hydrogens, -2 from the 2 permanganates, and -10 from the oxalate. And then on the right, we just have a +4. So that all checks out. And then we look at the elements. 16 hydrogens, 2 manganese, and then we have 8 oxygens. The oxygens are where you typically make a mistake because they're all over the place. You've got oxygens over here, which gives you 20, 5 times 4. And here you have 2 times 4 is 8, so that's 28. And the same thing over here. We have 8 in the water and 20 in the CO2, so we have 28 oxygens. 10 carbons on both sides. So everything checks out. And that's what's nice about balancing redox reactions. You get to the end, you have this nice, confident check. You know if you've made a mistake. So then if we evaluate these together, we have the oxalate, which is the oxidation reaction. How do we know it's oxidation? Remember oil rig. Oxidation is loss of electrons. So when you go past the arrow, we lost electrons. And reduction is gain. So manganese went past the arrow and it gained electrons. You're adding 5 electrons to the permanganate, and it's making the manganese ion. So we flip the sign. If we look this reaction up, it's going to be written backwards in the cell potential, reduction potential table, because it's all reduction. And it would have a negative 0.49. And so we flip the sign on this. And then we add those together. So this would be the electrical potential with 25C, 1 molar concentrations. The thing is, we've multiplied the oxalate reaction by 5, but we did not multiply the potential by 5. That's another huge mistake that people make. So they look at the reactions, they multiply by 5 and 2, but you never multiply those potentials. Okay, so the what's going on here when we multiply these reactions? Multiplying those reactions could give you higher current, but it's not going to give you a higher voltage. So voltage is like the height of a waterfall. Doubling these reactions is the width of the waterfall. You see, the voltage is just the height. How much potential energy that water has as it comes off that cliff. Okay, that's not going to change by doubling the amount of water. Doubling the amount of water is just making a wider waterfall. And so doubling the reactions just gives you more ions and more electrons. It ups the current, but it doesn't change the force on those electrons. And so this I just was reiterating that if you find this in the potential table, it's going to be a negative 0.49, and you flip it because it's an oxidation reaction. Now there's some information on line notation. It's just a shorthand for writing out these cells. So it's not that bad, but you've got to remember this key right here. It starts with the anode, goes to the cathode. It's in alphabetical order. So anode to cathode, AC, and then OR is also alphabetical order, and then anode and oxidation go together, and cathode and reduction go together. So if you can remember that order, this is how it's written out. And so then this is the anode. It's becoming copper 2+, which is an oxidation. This is the cathode. It's becoming silver to silver solid, silver ions to solid, and that's reduction. And so you could find this. If you had this line notation, then you would go to that reduction potential table and find these reactants and products in that table. And you would know which one's the oxidation because it's written first, and you know which one's the reduction because it's written second. And so they just have, sometimes you have electrochemical cells that have the electrodes participate in a reaction. But if you have non-metal reactants, you typically use an inert metal like platinum. And so this is actually the oxidation reaction, chlorate going to perchlorate, and this is the reduction reaction, permanganate going to manganese ions. So, and that just happens at the surface of the electrode. So that reaction gets real close to the platinum and reacts and gives its electrons to the platinum. And those electrons are transmitted through the circuit and come over here, and they reduce the permanganate ion at the surface of the electrode. And so that's what's happening. You can use line notation in the reduction potential table to do these kinds of calculations. I just want to scoot forward a little bit to get to corrosion. And so these kinds of reactions are really important in corrosion. So reactions with oxygen give you spontaneous cells. And so this is for aluminum metal becoming aluminum ion, producing actually aluminum hydroxide, incredibly spontaneous. And this is aqueous aluminum. And so we put aluminum in contact with water. We have aluminum pitchers, we have aluminum glasses, we have aluminum that holds water all the time, and yet this is a super spontaneous reaction.
I think it's the aluminum oxide that protect this reaction.
Yeah, protection or passivation is what they call it. So it is happening immediately. Aluminum is oxidizing, and then that oxide layer is forming a protective coating.
And I think that layer could be also used in the storage of concentrated sulfuric acid or something like that. So when they storage concentrated sulfuric acid, that oxidizing layer could also protect it from reaction with the acid and the aluminum. That's what I remember.
Okay, concentrated will dissolve it. It will dissolve that oxide layer. Because metal oxides are soluble in acid, and so that's how we brighten metal. Is we'll put it in acid called pickling solution, and it will dissolve a little bit of that. If you put it in strong, like sulfuric acid concentrated, it will actually fizz. It will actually heat up and generate gas, and it'll and make hydrogen ions and so on. So, but a mild acid will just dissolve a little bit of that oxide layer and cause the metal to look brighter. So this oxidation of the metal surface makes it look dull. So it has a surface finish effect, but it also eventually will pit. And pitting corrosion is the thing that we don't want to happen. So the main point is chloride makes this worse. If you have a water drop and chloride on the surface, that water drop and chloride will set up this galvanic cell, which can pit. So this is a water drop with chloride ions in it, and it will eat into the iron. Now, acid helps this along, you'll notice, and a lot of bacteria, as a byproduct of them using redox chemistry to power the cell, will produce acid as a byproduct. And so here you have a bacterium. If you put a bacterial colony here, it will drill a hole right through that metal. And it looks like a drill. If you get under a microscope and look at some of these pitting corrosion, especially a bacterial pitting corrosion, it's as if you took a drill and drilled right through the pipe or right through the valve. A lot of times it's in valves. They get in the threads of the valves and they set up a little bacterial colony and they use the metal potential to power the cell, and they produce acid, and that acid will eat right through the metal. So it's amazing. So that's part of corrosion prevention is not just controlling chloride, but also controlling bacteria.